Anyway, so here we are on chapter 5, or sorry, the fifth lecture, not chapter 5, the fifth lecture. We're starting chapter 3, and this is on the very important normal distributions. Excuse me. Of course, to understand what a normal distribution is, we need to understand what a distribution is. And we've talked a little bit about distributions, but we're going to go a little more in depth. And then we're going to talk about density curves. Density curves are essentially what we use to describe distributions. We're going to have a very important normal distribution, which is the subject of this chapter, and will play a role in pretty much every chapter from here on out to some extent. The 68, 95, 99.7 rule, which sounds very mysterious, but it's actually relatively straightforward once you understand normal distributions. The standard normal distribution, as we're going to see, there's infinitely many normal distributions, but the standard one is the one to rule them all. It's very Tolkien-esque, the one distribution to rule them all. Finding normal proportions, which is using the normal distribution to calculate proportions. Proportions are percentages, or how often something occurs relative to the total amount. The standard normal table, it's a good idea to be able to use the normal tables, even though your calculator will do everything for you. So we're not going to spend too much time on the table, although we will cover it. But we will spend more time on the calculator to make sure we use that. And then we have finding a value given a proportion. Again, that's related to the normal distribution. We'll all get into it. So this is a very cursory intro to the chapter. Personally, I hate intros like this because I am a very big believer in not mentioning something until you can understand it on the spot, as opposed to, oh yeah, we're going to learn later this, this, and this. And then you're like, okay, that tells me nothing now. So if you didn't get any of this or don't understand any of it, that's fine because it's stupid. So let's move on to the next slide, where it is more important and no longer stupid. And that is the concept of a density curve. So if you, for a second, scroll down to the next slide, slide 4, then what you have there is a histogram. Ignore that curve that we've drawn through the histogram. The histogram itself are the columns, right? We know how a histogram works. They're side by side, they're the same width, they're the same color, and the heights correspond to relative proportions or frequencies. So if 17 appeared in this width, we put 17 there, the height of 17. And, we've done this before. This should not be new. Hopefully there's no questions on the histogram aspect of this. If there is, of course, feel free to privately send a message. But what's important to see there is that we have drawn this curve through the histogram. And this curve is a density curve. And as you can see in the bottom left, it says the smooth curve closely approximates the tops of the histogram bars and provides a good description of the overall data pattern. So the curve that we draw is an approximation to the histogram, but it's a pretty good approximation, right? It's fairly representative of the shape of the histogram. And would you agree that if the bars of the histogram got smaller, so my width size got smaller, but my sample size was large enough that there was no gaps, so that every one of those bars had some elements, can everyone make sure they're muted? And the professor is the professor, that's me, hello, is kind of cutting off, and I think that is why. Ooh. Am I cutting out? Is everyone getting me cut out, or just that one? Oh, 2 people say I'm cutting out. So there is some static. Let's see, is there anyone here who's not muted besides me? I'm gonna mute him. And then we'll go to the next slide, and I will mute her. And the next slide, that's just 2 slides. So now everyone is muted but me, right?
It's good.
Is it better now?
Yeah.
Okay, so I think what we should take from this is that it wasn't my fault. That's really the most important thing. Whose fault it is, I don't care. It's just it wasn't mine. That's all that matters. Is everyone okay now? Does everyone hear me fine? Am I no longer cutting out? Fantastic. So back to the density curve. Excuse me. So the curve is a pretty good approximation to the overall pattern. Now, if you were to add up the number of outcomes that fell in each of those histogram bars, 17 in this one, 26 in this one, 108 in this one, and so on. If you add them all up, you would get the total number of outcomes, correct? That seems like a relatively straightforward idea, right? Since all the outcomes land in one and only one of the bars, if you were to add up all the bars, you should get the total number of outcomes, right? Yes, am I making sense here? Which means if each bar represented the percentage of outcomes that fell in that bar, so 12% in this bar, 14% in this bar, 6% in that bar, and so on. If I add up all those percentages, what should it get? What would all those percentages equal to? 6% here, 12% here, 18% here, 24% here. It would add to 100%, right? As someone just private messaged me, right? It would add to 100%. So the idea of the histogram bar is 2 things. One, all the bars go up. None of them are underneath the x-axis. That makes no sense to go down. How can it go down? It makes absolutely no sense because it represents the number of outcomes. It has to be positive. And the total amount underneath the bar, of all the bars added together, has to be 100%. So what we translate over to the curve that we drew are those 2 features. One, it can't go under the x-axis. And 2, the area under the curve has to equal exactly 100%. It has to equal 1. If the curve does not equal 1, it is not a valid density curve. Does that make sense so far? Yes, with me? Okay. So if we go back to the previous slide for density curves, it says we now have a toolbox of graphical and numerical methods for describing distributions. This is the previous couple chapters. What is more, we have a clear strategy for exploring data on a single quantitative variable. Remember, we have categorical versus quantitative. Categorical gets bar graphs and histograms. Sorry, bar graphs and pie charts. And quantitative gets histograms. And what's the other one? Anyone remember? Huh?
Stem and leaf plots.
Stem and leaf plots, right? Right? So, and then we had a time chart, which was something else. So step 1, always plot your data, make a graph, usually a histogram or a stem plot. We look for the overall pattern, shape, center, variability. Remember, shape was whether it's symmetric, right skewed, or left skewed. Center was either the mean or the median. Variability, either the 5-number summary with the IQR or the standard deviation. And then 3, calculate a numerical summary. Calculate a numerical summary is what I just said, right? Giving me the center and the variability, right? So you have, you make your picture, you look for the overall pattern and look for outliers, and then you summarize using either the median and the IQR or the mean and the standard deviation. That's what we learned in the first 2 chapters. So now we're going to add a 4th step. It says sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. In other words, if the number of observations was extremely large and the classes of my histogram got extremely small, then it would get closer and closer and closer to a smooth curve. Now, those of you who have taken some more advanced math, what am I referring to when I say,
Calculus.
what am I saying?
Calculus, integrals.
Integral. Okay, so those of you who have had calculus, I'm referring to what's called an integral process, where the size of my bars gets extremely small and I get more and more of them. If you haven't had calculus, which is not a prerequisite for this class, it's totally fine, but just be aware that a lot of these slides are going to be very hand-wavy, is the word we use in math. It's not very rigorous, but rather like you wave your hands and magic happens type thing. So there's not going to be as much rigor as I would like, but unfortunately it's what we have to do with. So let's look at slide number 5. So slide number 5 essentially summarizes what I just said, that the areas of the bars, which represents the relative proportions, has to equal 100%. Therefore, the area under the curve has to equal 100%. And if I want, for example, the percent less than, let's say, 6, then what I can do is calculate the area under the curve less than 6. Now, if the curve was a triangle, was a rectangle, maybe even a semicircle, then finding the area left than or right of a point is not really that hard. You can use basic geometry. But how do you find the area under a curve when the curve is some random looking function? So this is again a calculus question. Calculus 2, in fact, focuses really on area under curves. We're not required to have calculus in this class, correct? And as such, we need approximation techniques. We can't use rigorous techniques. We have to use approximation techniques. So, what are those techniques? Your table or your calculator. And we're going to learn both. Okay, so for now, let's look at the next slide. The next slide says, a density curve is a curve always on or above the horizontal axis and has an area of exactly 1 underneath it. It describes the overall pattern, and every possible outcome has to fall under it. So the bell curve shape goes to negative infinity and infinity. That obviously includes every possible outcome. Other ones might not. Okay, and we're going to see other ones as we learn more and more statistics. Okay, and it says caution. No set of data is exactly described by a density curve. Density curves are approximations. So in real life, for example, anyone here know anything about IQ testing? Anyone here ever get their IQ measured?
Like the how smart you are thing?
Like the how smart you are thinking, correct. Mine was negative 64. So I don't think it was negative 64, since the lowest it can possibly be is 0. And at that point, you'd be in a coma. So negative 64 might be a slight exaggeration. I failed it. Okay, well, I'm sorry to hear that. You can't really fail it. It's just a number. There's no anyways, it was just an example. But the fact is that the IQ is a normally distributed distribution whose center is 100 and whose standard deviation is 15. So even though the normal curve, the distribution, is not perfect, because in real life nothing can possibly be perfect, it is a great approximation because there's so many people who have taken the IQ exam that the data involved is so great that we have a very good approximation to the curve, to the point that we just say IQs are normally distributed, even though it's only an approximation. In this class, we're never going to have to worry about that. If you're given a problem and it says that you have a normally distributed curve or a normal distribution, don't worry, oh, is it only approximation? These numbers aren't going to work. Just go with it. Let's not make things more complicated than they already are, because statistics is already pretty complicated. But just be aware that no set of data is described exactly by a density curve. Now, if we look at slide 7, we have two different density curves. Okay, the first part, notice that both of them are above the x-axis, right? Both of them are above the x-axis. And although you can't tell by looking, the area under both of them is 100%, is 1. Otherwise, they wouldn't be distributions in the first place. The first one is symmetric. It's a perfect mirror image. Is the second one symmetric?
No.
No, in fact, it's skewed which way?
Right.
To the right.
It's skewed to the right. And remember what we said about means and medians. Means are non-resistant measures, which means means get pulled in the direction of skewness more than the medians as a general rule, which means if you look at the first picture, the mean and median are both exactly at the center by symmetry. Median, 50% to the left, 50% to the right, mean the average. But for the one on the right side, the skewed right distribution, the mean is pulled more to the right. And as you can see in the picture that the mean is slightly further to the right than the median is. Does that make sense so far? Yes? Any questions on that? Now's your time to ask. Okay, so now let's look at slide number 8, which talks about the difference between the mean and standard deviation that we've been using until now and a different mean and standard deviation, because there's two different types. There is sample means and sample standard deviations. So if you take a sample, what's the sample average and what's the sample standard deviation? The letters that we use for those, as we have been using, are X and S, although technically it's usually X bar and S, so that you don't just say X. X bar is equal to the mean, S is equal to the standard deviation for a sample. But if it's for the entire population or for the distribution, then we use Greek letters instead. Anyone know what Greek letter that is for the mean? It is a sound that a French cow makes.
Moo.
No, not moo, it's mew. I said a French cow. Are you listening? Not a regular cow. Never mind. It's mew. Okay.
Boo.
What was that?
Boo.
Boo?
Boo.
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 Okay, well, if you actually speak French, then now you're just making it worse for me, because I just pretend to speak French. I don't actually speak French. No parlez-vous français. So mu is what we're going to use for the population mean, and sigma, or technically lowercase sigma, because some of you might be more knowledgeable with the big capital letter sigma, lowercase sigma is what we use for the population standard deviation. And the question is, if I give you a normal distribution like I do on slide number 9, how can you tell, first of all, how can you tell where the center is? How can you tell where mu is located? This is the easy one, because if it's really normal, that means it has to be symmetric. And if it has to be symmetric, the mu is directly in the center. If you can't find the direct center, we have other problems. Okay, the mu, the center is literally at the peak. Not up here, because we're only looking at x values, but underneath the peak, right at the bottom. That's mu, x value. Sigma is a measure of spread. Okay, how spread out the data is. You don't go all the way to the right and left, because that's all the way to negative infinity and infinity. That's too far. Okay, so what we have to do is give us a geometrical method of determining how far to the left and right you go if you've moved precisely one standard deviation. So I want you to look at the graph on the left on slide 9. Mu is at the center, the peak, and they've gone to the right from mu precisely 1 sigma, 1 standard deviation. And my question to you is, by looking at the graph and only looking at the graph, how can you tell exactly how far to the right and left it is 1 standard deviation? What is the feature of that location that lets you know that it's precisely 1 sigma away from mu? And I'll give you a hint. It's a calculus concept. So if you've taken calculus, hopefully you recognize it. And if you have not taken calculus, you might have an intuitive grasp of it without the rigor of calculus. But when I say what the answer is, if no one gets it, or even if someone does, nothing to do with fundamental theorem of calculus, nothing to do with that. If you spot it, it's purely geometrical in nature. There's something about that location. The graph changes. When you pass that point, the graph to the left of it looks like one thing, and when you go to the right, looks like something else. And what precisely changes at that location is what I'm asking for. So does anyone want to give that a shot and tell me what occurs at that location so that to the left, the graph looks like one thing, and to the right, the graph looks like something else?
Are you talking about the delta x for when you do the rectangles? When
No.
you're inscribing it?
No, nothing to do with that at all.
Um,
That is not it. Someone says the curve goes up. Well, I don't know about that. Well, I'm not sure what you mean the curve goes up. The curve is at its peak, and then it goes down. And then when it hits that point, it still goes down. So the curve is going down both on the left and right side of that point. So going down doesn't seem to be a feature of the graph that changes at that location. I need something that changes at that location that makes it obvious where I can say, that's where sigma is. Nothing to do with limits. No, you're getting more technical. It's very geometric. Because just look at it and you'll know, or hopefully you'll know. It's halfway between that half. Well, technically the graph goes on forever, so it's not halfway between anything. So the answer is as follows. Starts to reach 0. No, it's going towards 0 the whole time. So here's the answer. And I'm going to invent a couple adjectives here. In the center of the graph looks hilly, correct? Like a hill, right? If you look at the center of the graph, it's hill-shaped. If you look on the ends of the graph, it looks more like a bowl shape. The way the graph is curved, on the ends, nothing to do with tangents. I'm giving the answer now. On the ends, the graph looks like a bowl, very bowl-y. But in the center, the graph looks like a hill, very hilly. Now that's actually an adjective. I didn't make that one up. So it's hilly in the middle, and it's bowl-y on the sides. Do you see what I mean by that? Let me share my screen for a second so I can kind of hopefully write this out a little bit. Annotate, draw. So here, the graph looks like a hill, correct? You see that? Very hilly. Whereas here, the graph looks more like a bowl. The sigma on this side and on this side is the point at which the graph changes from being like a hill to being like a bowl. From a calculus perspective, we would call this an inflection point. Inflection points. This is the worst writing program ever. That's an inflection. Oh my God, horrible. Inflection point. Does that make sense? Do you guys see that now? The difference between, so someone says when it goes from concave down to concave up. So that is the more technical way of thinking about it, concavity. Concave up, concave down. You don't need to know those terms. For us, it's going to be where it goes from being like a hill to being like a bowl. So that is the location from the center of 1 sigma in either direction. Does that make sense so far? Of course, yes, Anthony, same thing. Concave up to concave down to concave up is going to be the same thing. Yes, no, maybe so? Yeah, hopefully everyone feels that way. And notice that the graph on the right is very similar. It's much tighter, much sharper. Mu is still directly in the center, and the distance to the right or left up until that inflection point where it goes from being like a hill to being like a bowl is sigma. So if you want to describe the curve to me, you need to give me 2 things, 3 things technically. You got to give me that it's normal, so I know the kind of generic shape. You have to give me mu, so I know where the center is. And you have to give me sigma, so I know how far and how left you have to go to reach the point where you change from hilly to bowly. Does that make sense? So far? Any questions? Yes, no, maybe so?
Mu is the mean, right?
Mu is the distribution mean or the population mean. It's the center of the normal, the center of the curve. So it could be at 100, it could be 0, it could be -12, it could be 74. The center is anywhere. And then once you have the center, you have how far from the center you go to reach 1 sigma in either direction. And once you've given me those 2 and told me that it's normal, there's only 1 possible curve it can be. So normal, mu, sigma, you have uniquely determined the distribution. And any 2 people in the universe would agree on exactly what it says and what it does and how to calculate things. So next slide, slide number 10. A normal distribution is completely specified by 2 numbers. So 3 things total, normal. No, Andrew, there's no derivatives or concavity, no calculus in this class. It's just sometimes when something is related to a calculus concept, and some students have had calculus, I like to tie it in, but there's no calculus in this course. So normal, so now I know the generic shape, the mean, mu, so I know where the center is, and then sigma, so I know how spread out it is. If it's a big sigma, it's a very wide normal, and if it's a small sigma, it's a very sharp normal, okay? So those 3 things, normal, the center, and the center deviation, normal, mu, and sigma. You give me those 3 things, I know everything there is to know about the curve. And we're gonna start calculating with it. So let's look at slide 11 now. We're gonna start calculating things that have to do with the normal distribution. So first, the notation on top, capital N parentheses, mu, comma, sigma, N parentheses. That symbol, those symbols tell you everything you need to know. It's normal, what the mean is, and what the standard deviation is. So if I say, oh, we have an N of 5.2, so I just told you that it's normal. mu is 5, and sigma is 2. I've given you all the information that you need. Now, look at that curve on slide 11. First of all, do you agree that mu is where they claim it is? Okay, that's cool. But do you agree that mu is where they claim it is?
Yes.
Yes, it's directly in the center. Do you agree that sigma is what they claim it is? If I move from mu left and right a distance sigma, is it true that I do in fact reach the point where it changes from hill E to bowl E? Does anyone question that? Okay. The question now becomes, how much of the curve is between mu minus sigma to the left and mu plus sigma to the right? If I go to the left and right sigma, so if you look at the picture that they have there, the really dark blue area, okay, left sigma and right sigma. If I just look at that part, the question is, what percent of the entire curve falls between those two values?
68%.
Well, so this is the 68 in the 68, 95, 99.7 rule. The 68 says that 68% of my data is going to be between negative sigma and positive sigma. Does that make sense? Questions? Now, if you go 2 sigmas, if you go twice as far, the question is, what is the percent that's going to be underneath now? If you go 2 sigmas, 2 mu minus sigma, now you're further to the left, and mu plus sigma, now you're further to the right. Obviously, it's going to be more than 68% because there's more under the curve, right? So this is what the 68, 95, 99.7 rule says, that you now have 95% of the data is going to be within 2 deviations. And if you go 3 deviations out, mu minus sigma to mu plus sigma, you get almost all of the curve. And the question is, what percent would be there now?
99.7.
99.7%. This is the 68, 95, 99.7 rule. Now, I know of various rules in math. Someone texted me earlier one, he called it the fundamental theorem of calculus. The law of large numbers. This law, that law. Nothing beats the 68, 95, 99.7 rule in determining exactly what you do. Okay, it's the perfectly named rule. It literally gives you the numbers that you need to use in whatever problem you're working on. But remember what they stand for. 1 deviation, 68% from the center. 2 deviations, 95%. 3 deviations, 99.7%. By the way, these numbers are not exact. It's not exactly 68 or 95 or 99.7. In fact, if I use my calculator here, and I have my calculator do the one for 1 deviation, just to show you what it is, this is what my calculator gives me as 1 deviation left and 1 deviation right. Is that exactly 68%? Obviously not. It's slightly more than 68%. Where'd they get it from? Well, unfortunately, the only way you can get something like that is via calculus. And even calculus can't do it exactly. The curve is too complicated. So the only way we can do it is by using computer simulations, not simulations, but numerical approximations. So these come from computers approximating it for you. So let's do the next slide, slide number 12. It says the distribution of Iowa test of basic skills, the IPS vocabulary scores for 7th grade students in Gary, Indiana is close to normal. Remember, these are all approximations, so it's close to normal. Suppose we assume for the purposes of this test, or this example, that it's exactly normal and 6.84 1.55. What does a 6.84 tell me in that expression? N 6.84 1.55. What's 6.84?
I have a question, Professor. Sorry.
Yes, go ahead.
From the previous slide, the 68, 95, 99.7 rule is only used with the mean, correct?
Well, it's only used with normal, and it has to be from the center.
Right.
So,
which is the mean because it's going to be symmetric.
Well, not just symmetric. I mean, I can come up with symmetric graphs that aren't normal. This rule is only for normal curves.
Okay, thank you.
Do not use this rule for anything but normal distributions. Okay, there is a more fancy rule called Chebyshev's inequality. And Chebyshev's inequality is not as accurate as this because we have so much more information. And we're not going to use that. It's just throwing it out there just so you know that there is more math. The mean is mu, Melissa, they're the same thing. The mean is denoted by the symbol mu. So this should, letting you know that there's a lot of advanced stuff out there. But anyways, what does a 68.4, oh, someone answered that question. I'm sorry. I see people saying the mean or mu, and I understand now because we backtracked. 6.84 is the mean. It's the center of the distribution. What is 1.55?
Deviation.
That's the standard deviation. Okay. So if you look at the curve on the left, you'll notice that 6.84 is exactly in the center at the peak. And if you go 1 sigma to the right, so 6.84 plus 1.55 is 10.39. Right? No, what am I saying? 8.39. Sorry, I'm not sure where 10 came from. 8.39. And sure enough, the way it's labeled, if you go to the right 1.55, you get to 8.39. Do you not? Okay, and if you go left 1.55, 6.84 minus 1.55, then you get 5.29 apparently, assuming the math is correct. Do you agree? And if I want to go 2 sigmas in both directions, I would just subtract another 1.55 and another 1.55. So first I say sketch the normal curve. So you sketch a curve, you label the center as 6.84, you find where it switches from a hill to a bowl, at least approximately, because it's hard to do it by eye, but you get somewhere in the right vicinity. You label that as 6.84 plus 1.55 and 6.84 minus 1.55. Now we have the scale of the graph. Does that make sense?
Yeah.
So then they ask, what percent is between 3.74 and 9.94? So you have to ask yourself, how many deviations down to reach 3.74 and how many deviations up to reach 9.94? It's 2 deviations down, it's 2 deviations up. That's it, 95%, done, right? We don't got to use anything. It's 2 to the left, 2 to the right, 95%. That's a 68, 95, 99.7 rule. But the follow-up question is a little tougher. It says, what percent of the scores is above 5.29? What percent is above 5.29? So this one's a little, this one's a little tougher. So what's the mean again?
6.84.
6.84. And what do they want? They want above what number?
5.29.
Is that 1 sigma down?
Yeah.
Okay, so they want to know what's above 5.29. So they want to know all of this. Now, we can't directly use the 68, 95, 99.7 rule because this is not one of those three numbers. But I do know this. If I go one deviation left and right, just the center part, what's this part equal to? What percent?
68%.
Yeah.
That's 68%, correct?
Yes.
Which means outside of that is going to be what percent?
32.
32%, right? 68% inside, 32% outside, right?
Yep.
That 32% is split between this side here and this side here. So how much is here and how much is here?
16%.
So this side here is going to be 16%, and this side here is going to be 16%, correct?
Yep.
So how much to the right of 5.29, what's it going to be?
84%.
84%. So we're still using the 68, 95, 99.7 rule. It's just we got to be a little more ingenious with how it works. Does that make sense?
Yeah.
So you divide up the distribution of the pieces, figure out the percent for each piece, add up, subtract, do whatever you got to do to get the right answer. Yes, no, maybe so. Does that make sense?
Yes.
Yep. Okay. No, someone's confused. So what do you, I got how you got 32%, he says. Oh, well, the 32% is where? Where's the 32%? It's half here, half here. Correct? Okay, which means 16% on this side, 16% on this side, right? Okay, well, this is what we want. We want that part. 68 plus 16, 84%. Okay. So let's look at the next slide. This one doesn't have a lot of examples, like, you know, those little examples that I like to give. I don't see any. I'm scrolling down, 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 down. I'll have to come up with my own. In fact, let's do one right now. I'll give you guys one to do quickly. So let's do the following problem. Suppose you have an n. Somebody give me a nice simple number so I don't got to think too much.
12.
12. And now give me a sigma, another simple number.
3.
3. Wonderful. So we have a normal curve. That's what the n tells me. What does the 12 tell me?
Mean.
The mean, right in the center, is 12. And what does the 3 tell me?
The standard deviation.
Okay, so from the center, which is right here, I'm going to go to the right and left a distance 3. Now, I want you to tell me, approximately at least, where to stop for 1 sigma. I'm going to move along the curve. I'm going to go slowly, and you tell me where to stop when I've reached 1 sigma.
Stop.
Wait, right there.
All right, about here or so. Bill? Bull? Seems at least approximately correct, if not perfect. Which means if I go to the right and left 1 sigma, what number is this?
15.
15. What number is this?
9.
9. Once I have 1 sigma, I go the same distance. That's now 2 sigmas. What number is here?
18.
18.
What number is here?
6.
6. If I go the same distance again, that's 3 sigmas. Again, it's not, my graph isn't perfect. It should be the same height, of course, but what's here?
21.
21. And what's here?
3.
3.
Three.
Of course, these graphs do go on forever. So the question is, what percent is between 6 and 15? That's my question for you. What percent is between 6 and 15? I want you to think about that. Hopefully you can all see it clearly. I want you to think about that. What percent is between 6 and 15? And then if you think you have the answer, you can private message it to me. Kiara, I have an answer there, but I'm not sure how long ago it was from. So now, so you're saying it's that? Let me take a look. So that is not correct. Okay, I got it. Okay, so let's take a look. So far we have wrong. Anthony Arakelian, you were correct. Wrong. Anthony Arakelian, you're correct again. You just sent it to me twice for some reason, but it's still right. So great job. You're very proud of it. I get it. Wrong. I don't know. That's fine. Wrong. I don't know. Wrong. I don't know. I'm not sure. Not sure. No. Okay, so that's good that we stopped and did this rather than just going on to the next slide. A few people are close. I see some 80% and some 83%. Those are all close, but not close enough. Not close to an 84. So let me show you how I did it. One person got it, so that's fantastic. So here it is. We're going 6 to 15, correct? So let's start with the inside. 9 to 15. How much is the 9 to 15 going to be? What percent?
68.
68%, correct? So we already have 68%. And then we have a little more we got to figure out. Now, if I would go from 6 to 18, which is 2 to the left, 2 to the right, what percent would that be?
95.
That would be 95%, correct? Do we agree? Yes?
Yes.
Okay, which means that if I take the 2 and I remove the center part, leaving just these 2 pieces here, all 95, remove the center 68, how much would be between this and this? How much would those 2 pieces be?
27%.
27.
27, correct? Right? 95 minus 68, right? 27. Which means how much is just this piece?
13.5.
13.5. But isn't that what we want? This piece plus the center? So it's just those 2 added together, 81.5%. Did that make sense?
I have a question.
Yes, please.
So, wait, why did you subtract 68 from 95?
Because I wanted to figure out how much was in each of these individual pieces here. I knew that all of this part was 95 and the center part was 68. So if I remove them, I should get this part here.
Oh, all right. Thank you.
Which was 27, 13.5 in each. Now that I know this is 13.5, I can then add it to the 68 and I can get 81.5. Does that make sense? Yes, no, maybe so?
Yeah.
Wonderful. Okay, so we're going to have a calculator do this for us. Not, okay, I got a not really, which is fine. Let's spend a little more time. Not really, what's your question?
I'm just a little confused, but I think if we keep practicing it and I go over it on like my free, like on my own time, I think I'll be able to get it.
Oh, 100%. You know, just so you should know, one mistake people make is thinking that they need to come out of class with a full understanding. You go to class, you hear a lecture, ideally you want to understand as much as possible. But very rarely are you going to leave class and say, oh, I got this. Okay? But people expect that. And when they don't get it, they're very critical of either themselves or the instructor or even both, saying, yeah, this guy can't teach, she's horrible, I'm dumb, whatever the case may be, to come up with a reason why you don't get it immediately. It's just, that's just the way it is. You get as much as you can in class, and then out of class you go over it. That's why you have homework. That's why you take notes. Otherwise, they're just exercises for no reason.
Thank you, Professor. I have a question. Is there any like, way you can upload a picture of that, what you put on the whiteboard, to Canvas?
Well, it'll be on the video.
Oh, okay,
You
cool.
take a picture of it right now, actually.
Me or you?
Me, us.
Yeah. Like that? Is that what you mean? Just like take a snapshot or something?
Yes.
So I do have a text. I apologize. I still don't understand how you know that 6 to 15 is 95%. Look at 6. No, it's not. 6 to 18 is 95%. Not 6 to 15. 6 to 15 is what our question was. 6 to 18 is 95%, because 6 to 18 is 2 left, 2 right, isn't it? 2 deviations left, 2 deviations right. Right? That is the 68, 95, 99.7 rule. 2 deviations left to 2 deviations right is 95%. That you just accept because someone told you. Does that make sense? Yeah, but does it make sense though? I'm waiting for a yes.
Yes.
Okay. No, from the usually when someone sends me a text asking a specific question and I answer it, I look for that same person to then say, got it, thank you, understand, or something. Otherwise, I don't, you know, that's what I'm hoping for. So the final percent was 81.5%. Okay, that was the final one. Okay? Question, answer? All right, so when I look at these next slides that are coming up, it certainly looks like we are getting close to another topic. So I think this is a good time to stop lecturing for today. I'm going to stop recording.